All right, so my mic on? Okay. Hello, everyone. My name is Aruba, and I'm the programs coordinator at IndusSpace, and we are so excited for today's talk to hear more about innovations and work happening all around Canada. So thanks for being here, and let's get started. Quick reminder that this event is being recorded, so if there are any issues with that, please make sure to keep your cameras and mics off. The IndusSpace team acknowledges the various lands of Indigenous lands we reside on as an organization, including the traditional lands of the Huron-Wendat, the Seneca, and the Mississaugas of the Credit First Nation. If you'd like to follow us and stay updated on future events and initiatives, please follow us on social media at IndusSpaceCA and our partner for this program, Gen Action. Throughout the talk, if you have any questions, please submit them through Slido or use the Zoom chat. Don't worry about noting any of this. We will send a link for the Slido in the chat for you to submit your questions. Right now, we can begin with virtual introductions. So please let us know, what is your grade level? What fascinates you about Earth? And where are you tuning in from? Okay, I'll continue as answers come in. Quick ground rules. Please make sure to listen carefully, and if you have any questions, we will have time at the end to ask. Please make sure to keep your questions and comments short so we have enough time, and most importantly, have fun. This program is in partnership with Gen Action, along with over 30 other science centers across Canada. Our collective goal is to create and deliver climate action engagement programs to youth in every province and territory in Canada. Oh, Baravi, you can go ahead.
Thanks. Yes, so we're very excited as an organization to participate with 29 other organizations across Canada in bringing this program to Canadian youth. At IndusSpace, our vision is to empower youth in understanding how urban areas can contribute to the ever-increasing rates of greenhouse gas emissions. Living in large cities, similar to where we are based, has several factors that are things that we could think about and perhaps find ways to mitigate. And this is where we're excited to have this speaker series where our invited guests share a little bit about what they do and perhaps inspire us all to take some action. With that, I'll pass it back to introduce you to today's guest.
If you would like to stay till the end, we have a Kahoot. We'll send the link after the talk is done, so stay tuned for that. Without further ado, please welcome our final guest for the speaker series. Eric is the Director of Business and Development at GHGSat. He will discuss the role of Canadian space technology in fighting climate change. At GHGSat, he plays a key role in understanding of Earth and climate sciences as observed through satellites. Along with the goal for a brighter and greener future, GHGSat provides actionable greenhouse gas emissions data and insights, in particular, observations around methane emissions. We look forward to learning how observations from space help us understand our planet more and ways we can mitigate emissions. Welcome, Eric. The floor is yours.
Yoruba, thank you so much for that great introduction. As she mentioned, we at GHGSat use satellites to monitor greenhouse gas emissions around the world. And satellites are an advanced form of technology, of course, but in many ways, perhaps not as complicated as trying to get a PowerPoint presentation to work over Zoom. So I just tried to share my screen now, and can we confirm that, yes, I think that is working. And if I further press the magic button here, is this coming up correctly for everybody? The title slide, terrific. Well, it's really terrific. I'm really, really happy to be here this afternoon to talk about what I think is a rather interesting topic, that being how we use space technology as it directly pertains to fighting climate change. So maybe I'll start with a little bit about myself. So I'm an aerospace engineer by background. I'm a graduate of the engineering science program at the University of Toronto. And what got me interested in space originally was actually science fiction. So things like Star Wars and Star Trek, and it always motivated and inspired me. All that stuff about boldly going where no one has gone before and pushing out the frontiers and exploring what's out there. But beyond looking out into the cosmos, what has been really profound about our space activities is looking back upon the Earth. So this is the very famous Earthrise image of the Earth that was taken by the Apollo 8 astronauts in 1968. And this is, I think, one of the most iconic images of the early space age. The Earth as this pale blue, fragile marble in this darkest expanse of space, and the barren, lifeless moon in the foreground. And of course, in 1969, when human beings first set foot upon the moon, again, this was a very impressive historical and technological achievement. But what was really remarkable to me was, again, the images of the Earth as this frail little blue marble just off to the shoulder of the astronauts as they looked back across the gulf of space. And I really don't think that it is coincidental that the first Earth Day took place barely a year after the Apollo 11 moon landing in 1969. So the first Earth Day took place in April of 1970. And really, I would argue that it was our exploration of space and looking back at the beauty and fragility of the Earth from space that helped catalyze or bring forth this global awareness of what we need to do to protect our fragile planet and our environment. So the topic is greenhouse gas emissions. And when we talk about greenhouse gases, rightfully, everybody thinks first about carbon dioxide. And that's very important. But there is an equally, if not more important greenhouse gas, which until recently has not really gotten the attention that it deserves. And that greenhouse gas is methane. And the truth is that methane, over the first 20 years, over the first 2 decades that it's released into the atmosphere, actually has 83 times the global warming potential of carbon dioxide. And further to that, not only is it a powerful greenhouse gas, but in the past, it hasn't actually been well monitored and well tracked. And the reason for that is, if you think of where a lot of carbon dioxide comes from, it comes from, for example, the burning of fossil fuels. And that's obviously not a good thing, but it's actually relatively straightforward to track that. I know that there's a certain amount of fuel being consumed, I burn it, and you get this much carbon dioxide out the other end. Methane, it's a little bit different. It's produced in different industrial processes. It's, of course, a constituent of natural gas. And the systems up until now for helping us understand what methane we're actually putting in the atmosphere and what the concentrations are and emissions are worldwide, the quantification of that has been very challenging. But fortunately, we've made a number of great strides over the last couple of years, and I'll talk a little bit more about those in the next couple of slides and the rest of the presentation. So I said earlier that it was natural that as we go into space, it's an ideal platform for looking back at the Earth. So fortunately, there have been satellites for a number of years looking at greenhouse gases from space. One of the first that was dedicated to this to the greenhouse gas monitoring from space was a European Space Agency instrument called SCIAMACI. That's actually an acronym for something that I've forgotten, but it flew on a satellite called ENVISAT that operated in space between 2002 and 2012. So the first satellites that were actually dedicated to greenhouse gas monitoring were called GOSAT. These were launched by JAXA, the Japanese Aerospace Exploration Agency, back in 2009. And NASA has a series of instruments called OCO, the Orbiting Climate Observatory. So there was an OCO-2 that was launched in 2014. The OCO-1 was unfortunately lost in a launch accident. And there's also instruments on the International Space Station. For methane specifically, one of the key instruments is called TROPOMI, which is again on another European satellite, Sentinel-5P. And so, all of these satellites have been up there for a number of years, but most of these are, if you look at the picture here on the right, they're called the area flux mappers. And what this means is that they have the capability of looking at things at a very wide scale, over a region, over a country, over a continent, but at coarse resolution. So for the example of the TROPOMI instrument, it's capable of measuring things down to a resolution of about 5 by 7 kilometers and very high detection thresholds. So sort of tons of methane per hour. What we at GHGSat and the Canadian technology that we developed was a way to complement that by doing exactly the opposite. So using different satellites, smaller satellites that look at a very small part of the Earth. So in our case, about 12 by 12 kilometers, but at very high spatial resolution, looking at things rather than at the kilometer scale down to about 30 meters. And as you'll see in some of the pictures I'll show later, what that means is we can actually attribute an individual methane emission down to a facility, say a vent at a coal mine or an individual oil and gas well. And this is prior to what we did at GHGSat, a capability that did not yet exist in the world. So our company GHGSat was founded back in 2011 by these three dapper guys here. So Stéphane Germain is our CEO, my namesake Eric Edwards, the Chief Technology Officer, and François Rodigue, our Chief Financial Officer. And what motivated the creation of GHGSat in 2011, this was a bit of a key year because this was the year that two subnational jurisdictions announced a carbon pricing scheme to actually put a monetary cost on carbon emissions. And these two jurisdictions were Quebec, where GHGSat is headquartered. We're headquartered in Montreal and California. And what the realization was is that, well, it's all well and good to have these carbon pricing schemes, but it's not really going to work unless we can actually measure and quantify the carbon emissions themselves to see if people are actually paying fairly. Are they underreporting? Maybe they're paying too little. They may in fact be overreporting and paying more than their fair share. As the saying goes, you can't control and you can't do anything if you're actually not measuring. You can't manage something and you can't mitigate something that you're not actually measuring. So this was the rationale behind the creation of GHGSat, and ultimately the company's mission statement, if you will, is to become the global reference for the remote sensing of methane and other greenhouse gases as well, from basically any human-made source in the world. So who needs this service? The users and the customer base that call on GHGSat are very broad. One of the biggest and most important is the energy sector, the oil and gas sector. As I mentioned, methane rather is a constituent of natural gas, But there are other emission sources as well. So the waste management sector, decay in landfills, for example, can be big methane emitters if there are not gas recapture systems in landfills, for example. And this has important health considerations as well, because in many places, landfills are either in proximity or adjacent to urban and suburban areas. Mining is a big source of methane. For example, coal mining, this is vented, and this has implications not just for climate change in the environment, but the safety of people who work in these mines as well, because methane is not in itself toxic, but it is an asphyxiant, and there is a fire and explosion hazard associated with methane. And one of the other two fields here, agriculture, the joke about, burping and farting cows, I suppose, and power generation rather, hydroelectric dams, which we normally think of as a green source of energy, and they are. But what is interesting is that when there's degrading or rotting biomatter in the water, as the methane comes out of solution, when the water goes through the sluices of a dam, it comes out of solution, comes into the atmosphere. And what's been found is that these are in fact significant sources of atmospheric methane as well. So what does our technology look like? I talked earlier about some of the other satellites that blazed the trail for these. These were satellites that were put up by, for example, the European Space Agency or the Japanese Space Agency or NASA. Many of these satellites are huge. In the case of the GHGSat that I talked about from ESA, this particular spacecraft was literally the size of a bus. Ours are exactly the opposite, and you can see a picture of three members of our team there, garbed up in their clean suits as part of assembly integration of a test, and that is one of our real flight satellites in front of them. So these are what you've probably heard of as sort of the microsatellite class of spacecraft. So in our case, it's only about 15 kilograms, and as you can see from the picture, it's kind of like the size of a microwave oven. We like to think of these as sort of small and mighty satellites. So they don't look all that massive, but we like to think that they have a massive impact in terms of helping to fight climate. And it is remarkable that in such a small package, we're able to do these things like zoom in on methane emissions down to 30 meters resolution, which nobody else in the world can do right now. So we currently have 5 commercial operational satellites in orbit. There is a 6th one. It was a technology demonstrator that was launched in 2016. We have 6 more satellites that are scheduled to launch next year. So by the end of next year, we're going to have 10 operational satellites. The most recent launch was actually back in May of 3 satellites. And yes, that is my cat there being duly impressed as she watches the launch with me. And you might be curious to know that our satellites have names. So the first 6 satellites that we have up there are named Claire, Iris, Hugo, Luca, Penny, and Diaco. And where these names come from is these are the names of the kids of the company. So it's just a small thing we do to remind ourselves of the importance of our mission and what we're trying to do to help improve the planet we live on for future generations. Now, in addition to the satellite sensors, we actually also have adapted the technology to fly on an airplane as well. And so we've got 2 of these instruments right now. They're staged out of Calgary, and these complement the satellite coverage. So the satellites orbit about 500 kilometers up in space. As I said, the resolution is 30 meters, and they can detect methane emissions as small as about 100 kilograms an hour. Because the aircraft, being that much closer to the surface, typically flying at about 10,000 feet above ground level, the performance is sort of scaled or proportionally better. So the aircraft instrument is capable of detecting methane down to about 10 kilograms an hour. And the spatial resolution, depending on the altitude, is on the order of a meter. And so what I'll show you here is what the methane world looks like from our aircraft sensor. So this is two examples of measurements that were made of oil and gas infrastructure in the Delaware Basin region. This is a major shale gas play in the southwestern United States. And so you can see here that color scale in parts per billion of the concentration of methane, and what that 1 meter resolution can do, that we can literally pinpoint it down to an individual, not just a facility, but a specific part of the facility. So the concentration map here is overlaid. You see on this grayscale image is this monochrome context imager that's an integral part of the aircraft based instrument. So that was what the aircraft observations look like. I'll show a few examples of what the satellite observation looks like. So again, it's the same concentration scale here in parts per billion, with the lesser concentration being the darker color, going up to red being of the highest concentration. So I talked about I think I talked earlier about, burping and farting cows. So here's an example of that. So this is an agricultural feedlot that was taken by the Hugo satellite back in February of this year, of a farm outside of Bakersfield, California. And so the source rate that was measured here was almost 500 kilograms per hour of methane that this particular feedlot was putting into the air. A little bit closer to home, this is an oil and gas well in the Montney region of northwestern British Columbia near the Peace River. This was again taken by Hugo, being a very busy satellite, I suppose. This was taken in March of this year. And again, it was measuring a rate of about 500 kilograms per hour of methane. And one last example I'll show here. This is a liquefied natural gas terminal. I believe this is called the Curtis Terminal, that's in Queensland, Australia. And if you're able to see the picture on the right, again, that really high 30-meter resolution, we can pinpoint the source of that methane right down to a part of this otherwise sprawling LNG terminal facility. Maybe I'll add that the background picture there is not ours. So the methane data is what we record, and we overlay that concentration heat map just on regular commercial optical satellite imagery. So in this case, it's Mapbox or Bing or Google Maps or what have you. And this is really just to help people visualize and contextualize what the methane data is telling us. So all of these observations are nice, but ultimately what people need is information, is actionable intelligence. So we take data not only from our own satellites, but also from some of the public sector satellites that I mentioned earlier, the ones from the different international space agencies like ESA and others. So, we take data from our satellites, from aircraft, from these third-party satellites, bring it all together and work some machine learning and AI magic and get some actionable intelligence out of it. So what we're able to do are things like regional scale concentration maps, and then based on that, do time trending and identify where are the hot spots, where are the areas of concern within these geographical zones. And we can alert operators, alert people when we see elevated concentrations of methanes, or even flares. This is a major environmental concern, is that the practice of venting waste gas straight into the atmosphere. And this is there's new regulations coming online that will curtail or potentially even eliminate that in the future. And in some cases they're lit, which is a little better than just letting it go, but obviously you're still generating carbon dioxide if you light a flare. Ultimately there will be more stringent regulations in place, both in Canada and the US and other jurisdictions, on flaring activities. And the other neat thing that can be done with analytics is a bit of a predictive capability. So knowing the history of a particular site, how likely is it to experience a leak or problem in a certain time frame based on, for example, its production activities, past history, the age of the facility, and so forth. We can take all of these factors together and provide an estimate of when and where there might be a problem, so that operators can get ahead of the game and take a proactive repair activities. So I did promise Bhairavi that there would be no equations in this presentation anywhere, but I'll show one slide one graph rather. And what this is illustrating is an important principle of what these methane leaks, the characteristics of these methane leaks are like. And this goes back to an important paper, a meta study it was called, that was done by Dr. Adam Brandt at Stanford University back in 2016. And so what Dr. Brandt determined was that methane leaks, for example, in the oil and gas sector, follow what's called a long tail distribution. And what that means is that it's actually a small number of leaks that disproportionately put the most methane out into the atmosphere. So there is actually a little bit of good news there, because if we can concentrate our efforts into identifying and stopping those biggest leaks, we have an outsized climate benefit from doing that particular activity, rather than deploying our efforts sort of uniformly across all the sites, concentrate on the biggest problems first, get those fixed first, and realize the climate benefits as soon as possible. So what does that mean in terms of how we ought to use different technologies to monitor and ultimately mitigate things like methane? What I think it calls for is the recognition that no one technology or one solution, be it satellites or aircraft or something else, can do everything by themselves. What we need is to bring it all together in a collaborative way into basically kind of a multi-scale systems approach. So what we can envision is we have things like satellites monitoring on a very frequent basis, looking for the highest risk areas, looking for the biggest leaks, to find those leaks, big leaks, these so-called super or ultra emitters, as quickly as possible. So say, the first 50% of methane leaked by volume. Knowing that information, we can then deploy aircraft sensors to periodically survey those areas of interest that have been identified by the satellites as places that we should pay a little more attention to. So this airborne monitoring, be it with aircraft or with UAVs, would be done on a more periodic basis and help us eliminate the next 40% of methane emissions by volume. And finally, once we have the knowledge of where to look based on the satellites and the aircraft data, we can then judiciously and optimally send people exactly where they're needed to measure on site and to affect the repairs exactly where it needs to be done. So that's one type of collaboration. The other type of collaboration I'll talk about, and this goes back to those space agency satellites that I was talking about earlier, is what we do at GHGSat, these high resolution satellites, it's entirely complementary to what these wide field, low resolution satellites are able to pick up. And we really sort of tag team and work together. And the great example here is the Sentinel-5P Tropomi instrument of the European Space Agency that I talked about earlier. So since 2019, GHGSat has had a scientific collaboration with researchers at ESRON. This is the Dutch Space Research Institute and the Tropomi team over in Europe. And so what happens is Tropomi again measures very large scales over regional areas, over parts of countries and continents. And they'll say, hey, GHGSat, we found an area of higher methane concentration. Can you have a look there and see what the sources might be? And so this is where we now know where to point. We have GHGSat as sort of like a methane satellite microscope, zoom right in there with that 30-meter resolution and identify exactly where that methane was coming from. And I can illustrate some of this with a few case studies. So this was actually going back last year to February of 2021. This is exactly what happened. Is we were made aware through observations of a European satellite that there were elevated levels of methane in Central Asia. Specifically in the country of Turkmenistan. And the suspected source was actually at the time a natural formation called a mud volcano. So, hey, GHGSat, can you have a look at this mud volcano? Which we did. And to our surprise, we discovered it. Yes, there was a mud volcano there emitting, but right next door to the mud volcano was an oil and gas field. This was a major production area. And so what we were able to see in the field of view, this was the first time that we had observed 8 different methane plumes within one image like this. And these were very, very big emissions. So this was, one of these was on the order of 10,000 kilograms an hour, 10 tons, which I'm told had the climate impact of the emissions from 250,000 cars operating for 1 year. So knowing that this was going on, we contacted through various diplomatic channels. We got help from the government of Canada, diplomatic channels through the US government and European governments and the EU. So the operator of these facilities was made aware that there was a problem. And for a time, these emissions were actually shut down. Now, unfortunately, I wish there was a bit more of a positive end to this story. We've subsequently looked at Turkmenistan again, and unfortunately, a lot of these emissions seem to have started up again. So the efforts continue to try to ameliorate or help this particular environmental situation. The second example that I'll talk about here is a landfill. In this case, a landfill that is outside of Dhaka, the capital of Bangladesh. And I think, as I said earlier, the interest in landfills is that they are adjacent to, in many cases, in quite close proximity to human populations to urban areas. So back in April of last year, we detected a significant leak out of this sanitary landfill outside of Dhaka. And as a result of that, again, through various channels, the local authorities were contacted, and the government there stood up an environmental committee to look at these results and try to come up with mitigation solutions to address these leaks that were being emitted from the landfill. The last case study I'll talk about is a little bit more recent. You may remember back in September, there was the incident of the Nord Stream 1 and 2 pipelines that had a problem. and was leaking there in the North Sea. So the first media reports that something was going on, I believe, started going around the 26th of September. The next day, we at GHGSat immediately tried to task our satellites to have a look. Being the North Sea, we were hampered to some extent by cloud cover. This is, clouds are a challenge, not just for our satellites, but for every optical satellite. But finally, on the 30th of September, we were able to see the methane plumes in the North Sea. So we actually imaged 3 plumes on that day, and this is the biggest one here. So this one was emitting at 79 tons of methane an hour. And to give you a sense of the scale of that plume is almost 12 kilometers long. So this is one of the largest phenomenon that we'd actually ever observed from space. And again, this was a very recent thing, just back in September of this year. I'll start wrapping up by saying, I've talked a lot about sort of industries and operators and commercial activities. I'll say as well, and something we're very pleased about, is different mechanisms where our observations and our data can be put into the hands of scientists to not only to develop research, but to develop new Earth observation applications. So we back in April, we were officially announced as a third-party mission under the European Space Agency's EarthNet program. And what that means is that ESA, through this program, makes our data available for researchers in Europe. And we're very happy that most recently this fall, we got a contract from NASA for their analogous program, which is called CSDA, that's Commercial Smallsat Data Acquisition. We're going to start with an evaluation phase for that, but ultimately over the long term, what we hope is that through the CSDA process, our data will be made available through NASA to scientific researchers in the United States. What's up ahead? I talked a little bit about this earlier. So we've got 5 operational satellites up there now, plus the older tech demo, 6 satellites to be launched next year in 2 batches of 3. So roughly in the April and December timeframe, given the current launch schedule. We're also going to start looking at other gases. So our tech demo satellite was able to look a bit at carbon dioxide. We're planning a dedicated carbon dioxide satellite, and we're not standing still. So we're always doing internal research and development, looking at next generation sensors that not only look at different gases, but have even better performance than the ones that we have up there now. Just quickly to say that, the things that we're proud of is to address the priorities of society and of Canada as a whole, helping us meet our sustainable development goals, for example. And, really this is what gets us going in the morning, right? So I talked about our satellites being named after the kids of the company. It's these things that matter most to us. So, even only having 3 satellites back in 2021, we actually detected 143 million metric tons of carbon dioxide equivalent. And through those activities, we led or supported the mitigation of 2.3 million metric tons, which is the equivalent of taking about 500,000 cars off the road for a year. We've looked at emissions at over 100,000 sites in 47 countries on all the continents except for Antarctica. I think it's because those penguins are really clean down there, which is great. But it's all towards looking for the future. And I talked earlier about frontiers and going to the horizon. The horizon and the frontier that we want to see is a sustainable future right here on our very beautiful yet fragile blue dot in space. So with that, I'd like to direct everybody to our various social feeds, and I'd be happy to take any questions.
Wonderful. Thank you so much. I enjoyed the penguins comment at that point. It's like,
Penguins are
could
great.
they? Yeah, they are. Okay, so I'll invite anyone who hasn't already who would like to add more questions. We have the Slido link on our chat, but already I see a few questions, so we can get started with those. But definitely ask more if there are any. First question is, are the satellites the same size as a suitcase or maybe a washer? Can you talk a little bit on how best to visualize these satellites?
Well, let's see. I think they would be closer to a suitcase than a washer. I'm looking in our kitchen right now. Our washing machine looks pretty big. It's somewhere between the size of a microwave oven and a suitcase.
Okay. So another question was, how do you put the satellites in an orbit? Do they ever fall down?
That's a great question. So we put them in orbit with rockets, and these are rockets that are now available commercially. So companies like ourselves, it's kind of like buying an airplane ticket. You can buy a ticket for a company to put your satellite in space. So we've launched on a number of different rockets. Our first satellite, named Claire, which was the technology demonstration satellite back in 2016, it actually launched from India from a rocket called PSLV. Our second satellite, Iris, was launched on a European-Italian rocket called Vega. And subsequently, our other satellites have been launched on SpaceX Falcon 9 rockets. So in answer to the questions, do these satellites fall down? The answer is yes. So each of the satellites is designed to last for at least 5 years. They, in the case of Claire, as an example, it's lasted way longer than that. Satellites, generally, they're kind of like the Energizer Bunny. They just keep going and going and going. But because our satellites are so small, they actually don't have an engine, which means that over time, because even when you're in space, when you're 500 kilometers above the Earth, it's not a perfect vacuum, that there's still a few molecules of air up there, a very, very tenuous atmosphere. And that causes a drag on the satellites that ultimately brings them down, which it is not necessarily a bad thing, because there are international agreements that we don't want to leave satellites that are no longer working in space and prevent space debris and space junk. So, ultimately, it's actually a good thing for these satellites to come back into the atmosphere when their missions are finished.
Do they survive the trip back, or are they small enough that they would?
Oh, they're very small. So as I said, they're only 15 kilograms each. They're there's a size of a microwave oven, so there's no chance that anything would ever get down to the surface.
Okay.
Maybe as an interesting aside is, that was, of course, the completely the opposite of something like the International Space Station, which is absolutely huge and is the size of 2 football fields. And so one day, when its mission is over, it will have to be brought back down as well. And I would encourage people to maybe do a search and Google, what some of the interesting plans are to safely decommission and retire something that big.
Food for thought. Okay, so the next question is regarding some of the maps that you put out. There was a range of colors between the blues and the reds. So the question is, whether do we need to be concerned by those blue levels, even though they're on the lower end of the scale? Or should it only be like of concern if it's just the red spots?
Yeah, I think if you look at those scales, it helps us prioritize. So yes, I would say that the red scales are the most important, and those are the areas we have to target first. But ultimately, we need to try to clean it all up. So when we're done with the red scale, we should be moving down and cleaning up the blue scale as well. And this all comes back to what I said at the beginning of the presentation, because methane is such a powerful greenhouse gas, being 83 times more potent, having more greenhouse gas and planet warming potential than even carbon dioxide. Over the first 20 years it's released, we should sort of be going out there and cleaning up every single molecule of methane that we realistically can.
Mm-hmm. And then the final question, unless there are more that will be added, how high of an altitude do these satellites need to be orbiting at? You might have already answered that, but just to refresh our memory.
Sure. The satellites are in an orbit about 500 kilometers up in space, and I probably won't get into too much detail, but they're in a special kind of orbit called a polar sun synchronous orbit, and you can Google what that means. But basically, these satellites go from the pole to pole of the Earth, and as the Earth rotates underneath, what that means is that we can see almost every part of the surface of the Earth, except for a little bit of the part at the poles of the Earth. And the sun synchronous part means that every time we pass over a place on the Earth, the sun, the angle of the sun is the same. And this is actually important because our instrument needs the sunlight. It needs the reflected sunlight in order to be able to make an observation. So for example, our satellites would not be able to make an observation if there was too much cloud. I think I mentioned that as part of the Nord Stream challenge, and we can't make observations at night, for example.
Okay, we've reached the end of our questions, so thank you very much for answering those. I guess I'll just also do the official thank you for joining us, given your busy schedule. I'm glad it worked out that we could have you on today, and to everyone else tuning in. Thanks for joining us. And this is the last talk for this year. So we'll wish everyone a very happy, safe season's greetings. And we'll see everyone in 2023.
Yes, thank you so much, and happy holidays, everybody.
Thank you.
Thank
Bye.
you.
Happy holidays.